So in this lecture, we're going to discuss what is lexical analysis. So lexical analysis is the process of turning strings into tokens. So essentially, a token has a type and a value. So think of things like keywords, operators. They are token types, and then the value would be the plus symbol, the multiplication symbol. So again, in programming, when we say a keyword, what do we mean? We mean integer, we mean float, we mean double, right? All of those things, those data type names, are keywords. When you write them in your code, it's a keyword, right? So this is the job of lexical analysis. It goes through the source input and it produces token output, okay? Every token has a type and a value. And the part of the program that's responsible for lexical analysis is called Alexa, okay? So here's the lexical analysis example. We can see to the left we have our source program, which is a simple main function that sets an integer to 50. When it's passed through lexical analysis, through our Alexa, we get the following token output. We have a keyword with the value in it. That's our return type, yeah? We have an identifier with our function name. We have an operator with a left bracket, symbol with a right bracket, symbol with a left bracket. We have another keyword and then another identifier, then an operator, number, and symbol, and then finally the right bracket. So what are the benefits of lexical analysis? Well, we can easily identify source code, keywords, symbols, and operators, right? So it's less work for the parser, right? Because now the parser has to deal with tokens that it knows the type and value for, rather than having to parse through the actual source file, which would be a lot more work. Because if a parser is passing through the source file, it has a lot more to figure out. It has to figure out what's a number, what's an operator. All of the work that Alexa already does. So that's why we create Alexa, right? So there's less work for the parser. Token information is in the right format. So for example, if we come across a number, say 50, we know that in the source file that's a string, right? It's an ASCII 5 and an ASCII 0. Well, we take that and we convert it into an actual number stored in memory. So this is actually stored as an integer once it's gone through lexical analysis. So that means the parser doesn't have to worry about converting this into a number because we already do it during lexical analysis time. So another important thing, unnecessary information, such as spaces and tabs, can be discarded, okay? We don't have to worry about them, so there's less work for the parser to deal with. So here are the token types in our compiler. We have a token type of identifier. So this is used for all words with letters, underscores, and numbers that are not keywords. Okay? So keywords represent data types. So you can think like float, double, integer, long, and control procedure commands such as break, continue, return, stuff like that. That is a keyword in our compiler, okay? Operators are kind of self-explanatory, 5 plus 10. So plus is the operator, right? In our compiler, we will also have symbols. So these are quotes, semicolons, colons, and so on. Numbers are pretty self-explanatory. A numeric number, 50, 90, 100. Strings have data between quotes. So whenever we have a string in C, we call it a string, right? Double quote, hello world. Double quote, that's a string, right? So same with our compiler, that's a string. We're compiling C, so that's a string. So that has a token type of string, anything between these double quotes, okay? So token type of comments, these are for any comments in our C program, whether they be multi-line comments or normal one-line comments. They get created into a token type comment token. And token type new line, that just represents a new line in our program, okay? So back to the keywords, here are all of the keyword values in our compiler, okay? Unsigned, signed, char, short, integer, float, double, long, struct, union, and so on. Here are all of our operators, and bear in mind these operators can be joined together. So for example, the 2 right arrows to make a bit shift right, 2 left arrows to make a bit shift left, and then for indirection here, pointer access basically. We have the asterisks all joined together. In this case, a depth of 3 for a pointer, right? So numbers are this algorithm here. So if the ASCII character we read is above or equal ASCII 0 and the character is below or equal ASCII 9, then it's a number, okay? And a number token should be made. So here are all the symbols in our program. So we can see left bracket, right bracket, colon, semicolon, hashtag, backslash, right bracket, and an array bracket, okay? You might be wondering, why is the left bracket in the operator and the right bracket in the symbol? Well, technically, brackets are operators, okay? So that's why the left bracket's here. And then when we find a symbol with the right bracket, we know we're done with that operator, okay? So that's what that's about. Know that when it finds an equivalent right bracket symbol, it's done with that operator. But we'll discuss more on the parser in another lecture. I just wanted to get that across, why we have the left bracket here and the right bracket in symbol, because I know some of you might be wondering that. So an identifier is a capital A to a capital Z, a lowercase a to a lowercase z, followed by 0 to 9 and underscores. So, you know, this is the simple rules for variable names, function names, and structure names, right? So anything that is not a keyword and has these rules is an identifier, okay? So obviously if we type char, it can't be an identifier because that's a known keyword. So the keyword takes priority, okay? And then if it's not a keyword, it's an identifier, okay? So yeah, that explains lexical analysis. In the next few lectures, we'll be actually creating our lexa following these rules that I've described in this presentation. Thanks very much for watching, and I'll see you in the next lecture.